It's a pleasure to be here, and so I'm going to talk. My talk is divided into two parts, hopefully 15 or 20 minutes each, no longer. One is primary production, and in particular, gross primary production. And moving towards a gross primary production method that's only based on observations. Then I'll mention some things about some observation simulation approaches like the MODIS GPP product, Flex Tower approach, and then also the meteorologically driven Earth system models, thank you. And so one of the problems is there's no consensus, and frequently people, in some cases, agree on the annual cycle, but never on the amplitude. And we know that only observations capture disturbance and recovery, an integral part of the carbon cycle, and many of these are at coarser scales. So this is an example of all of these meteorologically driven Earth system carbon cycle GPP models. And you see, you would be hard-pressed to say which one is worse than the others. So this is for an area just north of the Gulf of Mexico, say in Mississippi or Louisiana, and it's a mess. These models just aren't too well formulated. Now when you go to a site, this is from the Howland Forest in Maine, so you have so you know there's no GPP in the winter. So here you get the annual cycle correct, but in terms of the magnitude, there's a huge range. So there's a huge opportunity to work on an observations-based method of GPP. Okay, so we started this. One of the questions is, well, what about all the vegetation indices? And so I've always been really curious about, especially the three-channel so-called Enhanced Vegetation Index of Alfredo Hertes. And so this also provided the opportunity for Jorge Pinzon and I to compare the NDVI to the two-channel Enhanced Vegetation Index, which was a fill-in for the three-channel when they found serious problems with it, as well as the EVI3. And we also evaluated a few other things. So one of the first things Jorge and I did was to look at how these three indexes, we processed the entire SeaWiFS record, because it's a small data set and you can process it from start to finish in a day, and then compared the NDVI with the EVI3 and the EVI2, and these are the mean values, and then we compare these against the red absorption. So this is the energy that drives photosynthesis. So this is the mean value, and then these are various quartiles. This is plus or minus 10%, 10%, 10%, 10%, on out like that. So it's a way of looking at the variation. What you see is there tends to be an asymptoting situation here. The EVI3 is terrible. It blows up at these values, whereas with the NDVI, it continues on up like this. So we thought, okay, this is one thing. Now let's look and make a comparison. If we take all the data for each of the growing seasons, north of the equator, south of the equator, and compare them, and lo and behold, the EVI3 turns Greenland and Antarctica green, because it's highly sensitive to, because it has in the denominator minus 7.5 times the blue band. Anything which increases the blue surface reflectance will increase the EVI. So this is why this is a terrible index. It's not atmospherically resistant. It suffers from aerosol problems. When they first processed the MODIS data, I'm told that the images came out, they were astounded that it turned Greenland green. Now, perhaps you know from your European history, or maybe not, that there was a Viking named Leif Erikson who got people to go to Greenland because he called it Greenland. And they thought, well, it must be a very good place with lots of vegetation, but no, it was just for advertising purposes. And I put the EVI3 in the same category. Okay, now this shows the EVI3 compared to its replacement two-channel algorithm, the EVI2 with red and infrared. These are all of the artifacts from snow, clouds, and then all of these values here are probably artifacts from atmospheric haze. Here's a comparison between the EVI2 and the NDVI. These are from climate modeling grid MODIS data, and you see that this is a huge population. This is almost 3,500 points, 3,400 points, and so these two indexes are very highly related. So now we go to comparing time intervals of NDVI and EVI2 and EVI3 and other indices to the time integral of chlorophyll fluorescence. So for chlorophyll fluorescence, we use Joanna Joyner's data. These are 40 by 80 kilometers. They're from the GOM-2 instrument, the Global Ozone Mapping Experiment, which flies on MEDOPS-2, the European Polar Orbiter. Now the cool thing about chlorophyll fluorescence is it's a flux. And if there's no chlorophyll fluorescence, plants are not photosynthesizing. This is sort of a leakage from the photosystem. It's kind of like us. When we metabolize, we give off heat. Well, when plants photosynthesize, they emit photons. Here's their distribution right here, something like this. But the problem is, to measure them, you have to measure them where there's no downwelling solar flux, or else you have a contamination of the emitted energy and the reflected downwelling solar flux. And so you have to make measurements within Fraunhofer lines where there's no downwelling solar flux. Because in the photosphere of the sun, different elements block the emission at those specific wavelengths. And so there's no downwelling solar flux here, here, or there. The problem is to make a measurement within a 1 angstrom wide band, you don't have a lot of photons. So you have to aggregate over large areas to have a strong signal. So that's why the GOM-2 data are 40 by 80 kilometers, which Joanna Joyner produces. And the GOSAT data, which are pretty noisy, I think are on the order of 10 kilometers, but they're noisy. So we use the chlorophyll fluorescence to define the growing season. No flux, no photosynthesis. So where you have evergreen vegetation, you can nail the start and the end of the growing season by chlorophyll fluorescence. It's unequivocal. Okay, so these are some chlorophyll fluorescence data from GOM-2, 40 by 80 kilometers. Joanna Joyner and I and a bunch of other people did a comparison. And this part, this is Russia. This, believe it or not, is the Caspian Sea at this scale. And there was a huge drought in 2010. So we made some comparisons there. So you see the difference for one of these areas. For area 1, I guess, let's see, where's area 1? This whole thing here is area 1. There were 200 GOM-2 pixels, but there were 12 million MODIS 250 meter pixels. So you see the spatial difference. This top panel are examples of the time and the GOM-2 fluorescence data for these 3 areas. And this is the drought year of 2010. And so it was much lower in all 3 areas. And the bottom are the MODIS 250 meter data for the same area, which show exactly the same thing. So this was encouraging, that because anytime a new thing is introduced, like chlorophyll fluorescence, a lot of people go wild and say, oh, it's great, it'll do all these things. And then you really need to check and make sure. And so, in essence, it appears to be, and we will show it is directly and very highly and linearly correlated to the vegetation indices. So these are 7 of our areas which we use for comparison. And then we have these 15 areas in the US. These are about 2 degrees of latitude by 2 degrees of longitude. And that's because to get a really strong chlorophyll fluorescence signal, we form these data into 8-day composites. You need this size area. And Joanna Joyner is one of the people on this study. Okay, so we compare all of the things we look at against the time interval for these 22 areas of solar-induced fluorescence from GOM-2. So here's the EVI2, and you see this linear relationship. You see a much noisier linear relationship for the EVI3. Here's the NDVI, and so it's very similar to the EVI2. Here's so this was with SeaWiFS data. Here we do the same thing, where we use MODIS climate modeling grid data, and here 0.93, 0.94 for the EVI2 and NDVI. We conclude that EVI2 and NDVI are functionally equivalent, if not identical. And then here's the same thing done only for the NDVI with MODIS 250 meter data. So then I thought, well, let's look at these time intervals of chlorophyll fluorescence, and let's compare them to some of the MODIS products and some other model products. So this is the MODIS 1 kilometer LEI product. So this is integrated green leaf area index over the growing season for these 22 areas. This is how things look. It doesn't look that good. And that's undoubtedly because the leaf area index product as an input of what the vegetation distributions are, types are, in each of these areas. And so therefore, that's probably pretty difficult to know, and it may change in time, so it's not that, it doesn't look that good. Here is the MODIS GPP product. It does fairly well, but it's at 1 kilometer in this linear fashion for these 22 points. So this is our metric for comparing things. Here is the FPAR product. It doesn't do as well, again, probably because it requires information about the vegetation distributions of vegetation types. So now we go to the MODIS 500 meter data, and things are looking better. And then we evaluated the index, which is the NDVI times the near infrared reflectance, which some people at Carnegie up the road proposed, and it does pretty well. And they attribute this to the near infrared data providing more information about the scattering volume in which photosynthesis occurs. Maybe this is true, maybe it's not. Anyway, so this is what we've done, but then we also look and compare these data to some of the Earth system models. And this is one of the better comparisons. This is the best comparison which we found. You explain about 70% of the variation compared to the time interval of chlorophyll fluorescence. And this is one of the worst ones where you only explain half the variation. So this is just kind of a guess. Anyway, so that's what we've done. Now one of our purposes in this is to look and see how can we go down to a finer spatial scale. This is just a crop calendar from some data which Brett Holman and I collected, I'm embarrassed to say, 39 years ago. Time flies. And so for winter wheat, where we went out on the ground with a handheld radiometer and measured things every good sunny day, so with about a 3 or 4 day sampling frequency. So the important thing, if you want to look at yield, you want to have data in this time period, because this is when the photosynthesis product is diverted into, in this case, wheat yield or wheat grain. And so knowing this crop calendar, you should put more emphasis here. Unfortunately, I can't find my notebooks with the raw data, because I would love to go back and reanalyze these, but I think I probably threw them away, or I'm not sure what happened to them. Anyway, okay, so when you form a time interval of the previous data, you only explain about 2/3 of the variation in terms of the grain yield, whereas in terms of total above ground dry biomass, you explain 80% of the variation. So this is why you want to be able to look at individual fields so you can improve your estimates of yield. And with 30 meter data or 5 meter data, you can do that. There's this cool data set, which I understand you're involved with. I think you're involved with this also in a major way. The harmonization of Landsat 8 and Sentinel-2A and 2B data now to 30 meters, to a 30 meter multispectral product, where you have an equatorial revisit frequency now of every 3.7 days. And if Landsat 9 joins the team in 3 years, it'll drop to 3 days. This is going to be a major accomplishment, because then you can look at individual fields and you can follow them through the time domain, and then perhaps use some of the numerical simulation models for crop yield for specific crops. Okay, so that's all I wanted to show. Oh, I'll just show this. Then someone said, well, how about the hyperspectral data? So there's a paper by Sean Serban in 2015 where he looked at photosynthetic capacity. And at the bottom, you see that there is this linear equation where you estimate one dependent variable from 7 independent variables. Well, there's no way this is going to scale across the landscape. It's too complicated. So I got really curious about that. So then I looked at the tables. So one of the other problems is only 70 pixels of average data were used for the previous figure. And so that's not much data. And this is just the predicted value versus the observed, where they divide the data set in half. So there are 35 points here. Anyway, so it's, and they used 35 of the points to develop the relationship, and then they applied it to the other half, and this is how it agrees with the one-to-one line. So I am, now perhaps this is an anomalous example, but I don't believe this should be used to say this is a way to get GPP from observations. It won't scale across the landscape. And these are just the various white ones which they used. Anyway, so our conclusions for this are NDVI and DVI2 are functionally equivalent. So we think red and near-infrared linear combinations are the way to go. We have red and near-infrared data now from the harmonized Landsat Sentinel data at 30 meters, and then Planet is going to try and do this at the 5 meters. This is the slide I showed there yesterday. It'll be cool if they pull it off, and this will result in substantial carbon cycle and food security advances. So that's the first talk. And now I think I'll go to the second one. Now, one of the things which I got involved in or with 3 or 4 years ago, Tom Wagner from NASA headquarters came to me and said, look, we need someone from NASA to work with the people in NSF on the use of commercial satellite data. And so he said, I want you to be in charge of it and do this. And I thought, well, okay. And he said, the first thing you have to do is go to the University of Minnesota and meet with Paul Morin, because they've been doing this for 4 or 5 years and are doing really well. So as soon as I went and saw what they were doing, they're working in the polar regions, I thought, wow, between the poles we can do a lot with these data. I'm not sure how or what you'll use to do it, but the opportunity is tremendous to be able to disaggregate to 50 or 40 or 30 centimeters. So Sundar Lee, our friend Sundar Lee at NASA headquarters, called me one day and said, hey, I want to submit a proposal to the Intel Challenge. Intel had a contest for big compute for scientific purposes. So I submitted something, I put Paul Morin on, so we are the co-PIs on this. We won this. Sundar supported us, and then the Intel Corporation paid for all the computing. And our goal was to look across the south side of the Sahara from 12 north to 24 north using commercial satellite data, and use these data to map and produce a quantitative estimate of above ground woody biomass and carbon. So to start on this, we're actually using data from 2008 now to 2017. We have maybe 700,000 images we start off with. We use the panchromatic band, which we use to pan sharpen the multispectral data. So we use the pan band and multispectral data. And then I'll show you how we try and analyze the data over this area from the Atlantic Ocean to the Red Sea. So far, things haven't worked, but I'm hoping that with machine learning and some better normalization of the data, that things will work. And if they do, we can do this globally for all the arid and semi-arid areas, which will address the question about the role of the semi-arid vegetation in the land carbon sink. Because we know that now things don't match up on the land, and some people say it's a tropical forest, some people say no, it's in the arid and semi-arid zone. So it's a way of at least eliminating one of those or seeing if it's case. What's the case? Because from first principles, you will expect, as carbon dioxide increases in concentration in the atmosphere, you will expect a greater effect in the hot, dry tropics than anywhere else, according to Graham Farquhar's work. Okay, so we come in, we form up the data. These are some old figures. We now have complete coverage everywhere across this zone. We form up the panchromatic data, and then we pan sharpen the multispectral data, and we use the NDVI because we need to determine where things are green at the 50 centimeter scale, and then to differentiate from dark objects like some geological areas which are very, very dark and very low in surface reflectance. Now we have several collaborators who are all based in Europe except for Patrick Gonzalez, who's at Berkeley. And so they actually have experimental sites. So we can tie back to these groups of people who we're working with, who have actual field data for specific trees. So then we can calibrate things and then go from there. Here's what the landscape looks like on the south side of the Sahara in the northern part of Senegal, right by the Senegal River. It's usually very sandy, slightly hilly because you have dune and remnants from previous geological periods, and you have scattered and discrete trees. So here's one of the areas. So we organize the data by UTM zones, which are 6 degrees of longitude across, and we're operating over 12 degrees of latitude. This is the one in Niger, Algeria, and Libya. And then here's what the panchromatic data look like. And so we map the tree crowns, and then we determine the centroid of the tree crown. This is the shadow, and then because we have data from November through March, we can look at the shadow, and from the centroid of the tree crown to the extent of the shadow, and simple trigonometry, you can tell how tall the trees are. Now, the reason you use the NDVI is because there are all of these features, which are not bushes, but they're rocks or tussocks or something, and they're not green for the most part. Perhaps one or two of them are. So this is why you use the NDVI data at 50 centimeters to get rid of a lot of false alarms. And so what we do is we come in again and we map the tree crown. We determine where the centroid of it is. We determine what the radius, and then from the shadow, we determine what the height is, and also what the area of the tree crown is. And we do this over between 10 and 11 million square kilometers of data. And the way I mentioned, we start off with 700,000 images, which we then organize. And so we've had 2 runs so far that both been, the first one was a total disaster. The second one, I think we felt we had a 30% accuracy. So we're getting ready now for the third run, but I personally think that machine learning offers a lot of advantages for what we want to do. Here's just the same thing with NDVI data. One of the things we found out, first of all, was if you weren't careful, there was actually that the shadows gave a very high NDVI value because more red light was transmitted, more near-infrared light was transmitted through, and very little of the red light. And so people said, well, we get this huge anomalous NDVI value, so we had to then to adjust things accordingly. So we realized we were looking at shadow. Anyway, so this is what we do. This is what we've been doing. Now also with the commercial satellite data, this is a comparison I did. I've done a little bit of work in Madagascar, and so each one of these green areas is one, or boxes is one Landsat 30 meter by 30 meter pixel. And so this is over a 2016 Digital Globe Worldview 1 image. And so you can see that this mapping of woody vegetation in Madagascar, at least in some areas, most areas, is off by plus or minus 1 pixel, which is what you expect. But it's a way of actually verifying and looking. So I think for the first time, and Rama mentioned Warren Cohen's paper on disturbance, and I think with the commercial satellite data under what you're doing, you can then tell and say, this is wrong or this is right. This is one example from Madagascar. Here's another example. So here is intact, a tropical, seasonal, or deciduous forest. This is a cleared area, and you can see individual trees. So using the commercial satellite data, I think for the first time, you can look at forest disturbance and recovery, or forest degradation, and you can answer that question very, very quantitatively, whereas right now we're just guessing. Here's an example from Madagascar. This is an area which was classified as deforestation in red. These are the Landsat pixels. Here's what it looks like with that removed. And you notice in the commercial satellite data, you see that the regrowth in this part of it is much more advanced than the regrowth in this lower part. So again, being able selectively to disaggregate to 50 centimeters can be very useful. So some of the timing considerations, it takes us about 12 CPU days to organize the data per UTM zone. And then when we process the data, it takes us, we have to have very substantial resources on the Goddard supercomputer. And so we're actually dealing in the areas we look at. So we organize the data into UTM zones, and each UTM zone is then disaggregated into 112 100 by 100 kilometer blocks. And then we disaggregate that into 25 by 25 kilometers, which means you have a 50,000 by 50,000 element array. And then you have to process these, so it takes a long time. And so if we throw 200 virtual machines at it, each with 5 processors, substantial amount of RAM, solid state disk drives, because you have to move a lot of data back and forth, you can process all 10 UTM zones in maybe a month. And as I said, our first 2 runs were unsuccessful. We're up to 30% accuracy. You could probably guess and do better. We're hoping each time we do it that we'll get better at it. And this is one thing which I hope we're able to work on with you using machine learning and collaborate. And if there are any other things you're doing where you could use commercial satellite data, let me know and we'll FTP them out. It's an open offer on all those fronts. Anyway, it's a pleasure to be here. I'll be happy to answer any questions, and thanks for your attention.